Hello dear viewers. I hope you are well. This is a voice, Gary, speaking to you as Buddy of Town's narrator. Yes, I have decided to give myself a name. It is a good name. In the last video, we discussed the Big Bang and quantum singularity stage at 10 to the minus 43 seconds after the singularity event. In this video, we will be discussing the Big Bang stage, quantum inflation. But first, we will revisit the Planck era and briefly discuss the stages leading to cosmic inflation. As previously discussed, the Planck Epoch, or Planck time, took place at 10 to the minus 43 seconds after the event which began the known universe. During the Planck Epoch, the temperature and average energies within the universe were so high that subatomic particles could not form. Even the four fundamental forces that shape the universe, that is gravitation, electromagnetism, the weak nuclear force, and the strong nuclear force, were combined and formed one fundamental force. Little is understood about physics at this temperature. Different hypotheses propose different scenarios. Traditional Big Bang cosmology predicts gravitational singularity before this time, but this theory relies on the theory of general relativity, which is thought to break down for this epoch due to quantum effects. In inflationary models of cosmology, times before the end of inflation, around 10 to the minus 32 seconds after the Big Bang, do not follow the same timeline as in traditional Big Bang cosmology. Models that describe the universe and physics during the Planck Epoch are generally speculative and fall under the category of new physics. Examples include the Hartle-Hawking initial state, string theory landscape, string gas cosmology, and the ekpyrotic universe. The Grand Unification Epoch took place between 10 to the minus 43 seconds and 10 to minus 36 seconds after the event which began the known universe. As the universe expanded and cooled, it crossed transition temperatures at which forces separated from each other. Like steam turning to water, the fields which define our universe's fundamental forces and particles completely change their behaviors and structures when the temperature and energy fall below a certain point. These phase transitions in the universe's fundamental forces are believed to be caused by a phenomenon of quantum fields called symmetry breaking. Spacetime symmetries are all around us in the everyday world: the right and left sides of an animal body, the circular disk of the sun and moon, a wallpaper pattern, or even a repeated musical rhythm. And symmetry has become a fundamental way of expressing the laws of physics. Symmetry breaking is an important process in both biological evolution and the evolution of the universe as it moves in time through different eras. Wherever structure becomes more complex, symmetry, or at least the original symmetry, is lost. It is this breakdown of symmetry that theorists are trying to understand in reverse, because at the beginning of the universe, it was perfectly symmetrical, and as it cooled, symmetry breaking took place, creating the more complex and varied world of particle physics. In everyday terms, as the universe cools, it becomes possible for the quantum fields that create the forces and particles around us to settle at lower energy levels, and with higher levels of stability. In doing so, they completely shift how they interact. Forces and interactions arise due to these fields, so the universe can behave very differently above and below a phase transition. Assuming that nature is described by a so-called grand unified theory, the Grand Unification Epoch began with a phase transitions of this kind, when gravitation separated from the universal combined gauge force. This caused two forces to now exist, gravity, and an electrostrong interaction. There is no hard evidence yet that such a combined force existed, but many physicists believe it did. The physics of this electrostrong interaction would be described by the Grand Unified Theory. Ended with a second phase transition, as the electrostrong interaction in turn separated, and began to manifest as two separate interactions, called the strong and the electroweak interactions. The Grand Unification Epoch ended at approximately 10 to the minus 36 seconds after the Big Bang. At this point several key events took place. The strong force separated from the other fundamental forces. It is possible that some part of this decay process violated the conservation of baryon number and gave rise to a small excess of matter over antimatter. This phase transition is also thought to have triggered the process of cosmic inflation that dominated the development of the universe during the following inflationary epoch. The next epoch is the Electroweak epoch, which took place between 10 to the minus 36 seconds, or the end of inflation, and 10 to the minus 32 seconds after the Big Bang. Depending on how epochs are defined, and the model being followed, the Electroweak epoch may be considered to start before or after the Inflationary Epoch. In some models it is described as including the Inflationary Epoch. In other models, the Electroweak epoch is said to begin after the Inflationary Epoch ended, at roughly 10 to the minus 32 seconds. According to traditional Big Bang cosmology, the Electroweak epoch began 10 to the minus 36 seconds after the Big Bang, when the temperature of the universe was low enough, 1028 Kelvin, for the electronuclear force to begin to manifest as two separate interactions, the strong and the electroweak interactions. The exact point where electrostrong symmetry was broken is not certain, owing to speculative and as yet incomplete theoretical knowledge. Inflationary epoch and the rapid expansion of space is the next stage after the event causing the creation of the universe. The cosmic inflation theory was born as an extension of the Big Bang theory to explain how the universe was created, and how everyone and everything got here. Astronomers observe that the universe is expanding and has been doing so for about 13.8 billion years. At the very earliest times, too early to see directly, the leading idea is known as cosmic inflation. American physicist Alan Guth proposed the theory of cosmic inflation in 1981. Since then, cosmic inflation has become an important concept in the study of the early universe, to the point that it's currently integrated into the standard model of cosmology that embraces the Big Bang theory. This theory supposes that the embryonic universe abruptly ballooned in size. Such a growth spurt would have ironed out any curves and warps in space, thus explaining the geometry of the universe today, and left behind slight non-uniformities that seeded galaxies. The inflationary epoch and expansion of space took place just before 10 to the minus 32 seconds after the event which began the known universe. At this point of the very early universe, the metric that defines distance within space suddenly and very rapidly changed in scale. Note: in general relativity, the metric tensor, the metric, is the fundamental object of study. The metric captures all the geometric and causal structure of spacetime, being used to define notions such as time, distance, volume, curvature, angle, and separation of the future and the past. So, within 10 to the minus 30 seconds, the universe enlarged by a factor of at least 1025 in every direction. It expanded at an accelerated rate, pulling regions of space apart faster than the speed of light. This change is known as inflation. Although light and objects within spacetime cannot travel faster than the speed of light, in this case, it was the metric governing the size and geometry of spacetime itself that changed in scale. Changes to the metric are not limited by the speed of light. There is good evidence that this happened, and it is widely accepted that it did take place. But the exact reasons why it happened are still being explored. So a range of models exists that explain why and how it took place. It is not yet clear which explanation is correct. In several of the more prominent models, it is thought to have been triggered by the separation of the strong and electroweak interactions which ended the grand unification epoch. One of the theoretical products of this phase transition was a scalar field called the inflaton field. As this field settled into its lowest energy state throughout the universe, it generated an enormous repulsive force that led to a rapid expansion of the metric that defines space itself. Inflation explains several observed properties of the current universe that are otherwise difficult to account for, including explaining how today's universe has ended up so exceedingly homogeneous, similar, on a very large scale, even though it was highly disordered in its earliest stages. It is not known exactly when the inflationary epoch ended, but it is thought to have been between 10-33 seconds and 10-32 seconds after the Big Bang. The rapid expansion of space meant that elementary particles remaining from the grand unification epoch were now distributed very thinly across the universe. However, the huge potential energy of the inflation field was released at the end of the inflationary epoch, as the inflaton field decayed into other particles, known as reheating. This heating effect led to the universe being repopulated with a dense, hot mixture of quarks, antiquarks and gluons. A quark is a type of elementary particle and a fundamental constituent of matter. Antiquark is the antiparticle of a quark, while quark is in the Standard Model, an elementary subatomic particle which forms matter. Quarks are never found alone in nature and combine to form hadrons, such as protons and neutrons. A gluon is an elementary particle that acts as the exchange particle for the strong force between quarks. It is analogous to the exchange of photons and the electromagnetic force between two charged particles. Gluons bind quarks together, forming hadrons such as protons and neutrons. In other models, reheating is often considered to mark the start of the Electroweak epoch, and some theories, such as warm inflation, avoid a reheating phase entirely. In non-traditional versions of Big Bang theory, known as inflationary models, inflation ended at a temperature corresponding to roughly 10 to the minus 32 seconds after the Big Bang, but this does not imply that the inflationary era lasted less than 10 to the minus 32 seconds. To explain the observed homogeneity of the universe, the duration in these models must be longer than 10 to the minus 32 seconds. Therefore, in inflationary cosmology, the earliest meaningful time after the Big Bang is the time of the end of inflation. After inflation ended, the universe continued to expand, but at a much slower rate. The volume of space we observe today was a quadrillionth the size of an atom when inflation began. During inflation it grew to the size of a dime. In the billions of years since then, space has continued to expand but at a mellower pace, allowing structures such as galaxies to form. About 4 billion years ago the expansion gradually began to speed up again. This is believed to be due to dark energy becoming dominant in the universe's large-scale behavior. It is still expanding today. The theory of cosmic inflation proposes a period of extremely rapid exponential expansion of the universe during its first few moments, starting at 10⁻36 seconds after the Big Bang singularity. Astrophysicist Ethan Siegels explains the term exponential expansion as follows. If your universe were filled with radiation, it would expand like the square root of time. The distance between you and this particle scales as asymptotic T1/2. If your universe were filled with matter, it would expand like time to the 2/3 power. The distance between you and this particle scales as asymptotic T2/3. But when your universe inflates, space expands exponentially, like asymptotic EHT, where h is the expansion rate of the universe. Simply put, the universe developed from a tiny speck, hypothetically containing the entirety of space, into something much, much bigger. Cosmic inflation explains how this occurred uniformly in spite of the rapidness of the process. Inflation was invented to explain a couple of features of the universe that are really hard to explain without it. So what problems does cosmic inflation resolve? Even though the Big Bang theory seemed quite plausible because of the discovery of the CMB, there were a few problems with it. In other words, what the Big Bang theory predicted would happen in the universe as it grew has not actually happened. The three major problems with the Big Bang theory include 1. Flatness. The universe that we live in currently appears to be flat. The flatness problem basically questions why the universe density is so close to the critical density. The critical density is the average density of matter required for gravity to halt the expansion of the universe. A universe with the critical density is said to be flat. However, according to Big Bang cosmology, the curvature of the universe should grow with time. But, the Big Bang theory predicted that there would be at least some curvature to it due to initial irregularities in its shape that would become more prominent during the 14 billion years of growth and change. Also, Einstein's general theory of relativity states that mass, such as that created by the Big Bang, should ultimately bend both space and time, creating a more curved universe. 2. Homogeneity. The Big Bang theory would create a universe in which there were many variations in temperature in different areas due to the vast distances involved and the lack of time for heat energy to transfer from one place to another. However, in reality, the universe, specifically, the cosmic microwave background, CMB, has a very uniform temperature in all directions. Why is that the case? The homogeneity problem is also referred to as the horizon problem because it questions why the universe is uniform in all directions, a property called isotropy. Many distant regions of space in opposite directions are so far apart that, assuming a standard Big Bang expansion, they could never have been in causal contact with each other. This is because the travel time, for light, between them exceeds the age of the universe. Yet research has demonstrated that the cosmic microwave background temperature is uniform throughout the universe. This tells us that these regions must have been in contact with each other in the past. How can extremely distant zones in space have their matter and radiation distributed so evenly when they're too far apart to have been in casual contact with each other? Again, cosmic inflation is the answer. Its integration into the Big Bang theory implies that there was a stage in the early universe when everything was much closer. For the universe to get inflated or expanded, it must have been deflated or contracted first. The distant zones of space obtained the same temperature while interacting with each other before the inflationary process began, and kept it after it finished. 3. Magnetic Monopole. The Big Bang theory predicts a universe in which the energy isn't distributed evenly, which means it would have a lot of magnetic monopoles in the coldest, most frozen parts of it. Magnetic monopoles are hypothetical particles that consist of an isolated magnet with only one magnetic pole. These are believed to exist at very low temperatures. However, they are not seen in the universe as the theory predicts. Why not? Inflation allows for magnetic monopoles to exist, but only if they were produced before the period of inflation. During inflation, the density of monopoles dropped exponentially, so their abundance also dropped to undetectable levels. The cosmic inflation theory was developed by particle physicist Alan Guth during the early 1980s to deal with the three problems presented by the Big Bang theory. He theorized that the reason why the universe appears to be flat is because of the extremely fast rate at which it grew. It may have doubled in size every 1/10⁻35 seconds, and after doing this many times, the universe would appear to be flat even if it was curved. This rapid expansion of the universe would also explain why we cannot observe anything but uniformity in its energy distribution. As for the magnetic monopoles, they may still be out there, but were formed too long ago and are simply too far away to find. There was much indirect evidence to support the cosmic inflation theory before direct evidence was found. A lot of this came from the Wilkinson Microwave Anisotropy Probe, or WMAP, which is a NASA Explorer satellite mission launched in 2001 designed to study the characteristics and properties of the universe. Data from the WMAP has shown that the observable universe is indeed flat and rapidly expanded. The data also explains how fluctuations in the density of cosmic matter led to the formation of stars and galaxies, and how the temperature of the CMB is relatively uniform. Between 2001 and 2010, NASA's unmanned spacecraft Wilkinson Microwave Anisotropy Probe, WMAP, studied the cosmic microwave background and produced data indicating that the universe is, in fact, relatively flat. But the process of cosmic inflation would account for the near flatness that WMAP detected. The inflaton is a theoretical particle that would have shoved space to a gargantuan size in a fraction of a second before leaving the universe to expand far more gradually under its own cosmological constant. The inflaton's potential energy can cause the universe to expand at an accelerated rate. In the process, it can smooth and flatten the universe, provided the field remains on the plateau long enough, about 10 to the minus 30 seconds, to stretch the universe by a factor of 1025, or more, along each direction. Inflation ends when the field reaches the end of the plateau, and rushes downhill to the energy valley below. At this point, the potential energy converts into more familiar forms of energy, namely, the dark matter, which is hot ordinary matter and radiation that fill the universe today. The universe enters a period of modest, decelerating expansion during which the material coalesces into cosmic structures. Inflation smooths the universe just as stretching a rubber sheet smooths its wrinkles, but it does not do so perfectly. Small irregularities remain because of quantum effects. The laws of quantum physics dictate that a field such as the inflaton not have exactly the same strength everywhere in space but that it undergo random fluctuations. These fluctuations cause inflation to end at slightly different times in different regions of space, heating them to slightly different temperatures. These spatial variations are the seeds that will eventually grow into stars and galaxies. A prediction of inflationary theory is that the variations are nearly scale invariant. That is, they do not depend on the size of the region. They occur with equal magnitude on all scales, and confirmed that the spatial variations in energy in the early universe were nearly scale invariant. The theory of cosmic inflation has been criticized by a number of scientists, including one of its co-founders, American physicist Paul Steinhardt. In 2013, Steinhardt and his team analyzed data collected by the Planck satellite and concluded that this seemed to rule out the simplest inflationary models. The more complex ones, however, required more parameters, more fine-tuning of those parameters, and more unlikely initial conditions. Steinhardt called it the unlikeliness problem. He even talked about bad inflation and good inflation. Not only is bad inflation more likely than good inflation, but the absence of inflation is also more likely than not, he explained in his paper titled The Inflation Debate. The unlikeliness is supported by scientists like British mathematician Roger Penrose who, according to Steinhardt, applied thermodynamic principles to count the possible starting configurations of the inflaton and gravitational fields. Some of these configurations lead to inflation and thence to a nearly uniform, flat distribution of matter and a geometrically flat shape. Other configurations lead to a uniform, flat universe directly, without inflation. Both sets of configurations are rare, so obtaining a flat universe is unlikely overall. Penrose's shocking conclusion, though, was that obtaining a flat universe without inflation is much more likely than with inflation. The theory of cosmic inflation has also been accused of being too flexible, meaning that it can pave the way for so many outcomes that there is no way to disprove it, or to prove it. But the data seem to indicate that cosmic inflation doesn't only tie up the loose ends of the Big Bang theory, it may be correct, at least in some form. It has become widely accepted by many physicists because it has also led to new predictions which have been observationally confirmed. As Ethan Siegel says, inflation has literally met every threshold that science demands, with clever new tests becoming possible with improved observations and instrumentation. Whenever the data has been capable of being collected, inflation's predictions have been verified. When cosmic inflation came to a sudden and still mysterious end, the more classic descriptions of the Big Bang took hold. A flood of matter and radiation known as reheating began the process of populating our universe with the stuff we know today: particles, atoms, stars, galaxies, and so on. This was all still within the first second after the universe began, when the temperature of everything was about 10 billion degrees Fahrenheit, 5.5 billion Celsius, according to NASA. The cosmos now contained a vast array of fundamental particles such as neutrons, electrons and protons, the eventual building blocks or raw material for everything we see today. So what did Buddy from town learn today? The early stages of the Big Bang result from theories which are examined and tested over and over to confirm or criticized findings. The more confirmations or verification, the more solid the theory. Whenever the data has been capable of being collected, inflation's predictions have been verified. Scientists are continuing to uncover new information. There is more clarity about how the eventual building blocks or raw material for everything we see today formed. In our next video, we will continue looking at key stages of the Big Bang. If you would like to follow along to see Buddy from town become Buddy of Singularity, please click subscribe and a like would be appreciated. Until next time, dear viewers, keep looking up and looking back, way back.